All right, so today we're going to start on the next module. You'll still be working on file I/O this Friday in your lab, in your hack. We are starting to grade the string lab, or the string hack, I should say. And we are noticing a lot of failures, especially on length split. So you definitely want to go back there and fix those issues, because you're definitely going to want to use that on your next hack. I mean, you can do it other ways, but if you have that function available to you, that's really going to help you on the next hack. You have to split apart like a DNA string into trigrams, and then you translate it to a protein sequence, I think it is. So keep that in mind. All right. We are online, so if you have any questions, make sure that you are posting to Piazza or to the YouTube live stream here. All right. So with our demonstration last time, we developed we took a CSV file, a comma separated value file, that contained just data about, say, people, right? Their NUID, the cities, the state, and their office, right? And then we converted that into JSON, okay? But it was kind of hacky in that we had to go line by line, and we had to split out each one of those pieces of data without any regard to keeping them together, right? That a person is a first name, a last name, an NUID, a city, state, and zip, or office, right? A person, at least as far as this data is concerned, is 6 different pieces of data, right? If we kept all of that in different arrays, for example, I had 4 people in my array here, I would have to maintain 6 different arrays with different pieces of data for each. You'll see this on Friday when you have to to parse some data related to states. A state is a name, an abbreviation, and a population, right? 3 pieces of data. You'll also be doing some data with Major League Baseball teams. And there it's the team name, salary, a total salary, their wins, their losses, a couple of other pieces of data. But you've got multiple pieces of data that you want to treat as one logical unit. That's where encapsulation comes in. What we can do in programming languages is define a user-defined type where we can put in multiple pieces of data into one logical unit. For C, that's going to be structures, okay? So built-in types such as int, double, and char are not enough, right, to model real-world data, right? Not everything is a number, not everything is a string, right? Everything has multiple pieces of data. Real-world entities have multiple pieces of data that should be grouped together, right? If we keep track of these multiple pieces of data in different variables, right, then we start to lose track of them, right? And our examples that we've already seen are, say, the person data, person office data, right? In your lab this Friday, you'll see like baseball teams, right? States, right, etc. Right? All have multiple variables associated with them. Right? If we don't keep them together, then we've got a lot of bookkeeping to make sure that this population is associated with this state over here. So if we keep track of them in different arrays and we ever swap them because we want to sort them or something like that, then we need to make sure that we have those 2 associations. Or better yet, we can define our own user-defined type, right? In C, you can define a structure. Right? A structure allows you to group multiple pieces of variables together into one logical unit, right? And treat it as one logical unit, okay? This is generally referred to as encapsulation. Right? You encapsulate all of these pieces of data together into one thing, right? Now, encapsulation is more general than that. Encapsulation involves the grouping of data, right? 2, the protection of data, and 3, the grouping of functionality that acts on that data. That's what true encapsulation is. However, that's more of an object-oriented programming concept. So if you've had any exposure to object-oriented programming languages where you use, say, classes, then a class is the way to encapsulate multiple pieces of data together. It also is a way to put in functions that act on that data, and also the protection of that data using these keywords called private, public, protected maybe, etc. C predates object-oriented programming by at least 10 years. And it's not an object-oriented programming language. So in that sense, C is only supports number 1. Right? It only supports the first part of encapsulation. And if you want to, you can call it a weak encapsulation. Right? So C only supports number 1, the grouping of data. Right? It's weak encapsulation. Right? Otherwise, other languages do have strong encapsulation. So let's just get right into it by defining our first structure, defining structures. Right? So this obviously was, like, say, a faculty member or something like that. So let's just go ahead and use that as our basis for this example. Okay? I'm going to come over here to demo, and before I go into main here, let's go ahead and define this structure that models a faculty member. Okay? And the way that I do this is using type def. That's short for type definition. Where have you seen that before? Enums, enumerated types. But instead of an enumerated type now, I want to define a structure, struct. Right? And because we don't like writing things out in 1970 or whatever it was, if you could save 3 characters, URE, you did it, right? Because you were paying by the byte. And so it's type def struct. Okay? Opening curly bracket, closing curly bracket. Now, ultimately, this structure is going to model a faculty member, so what should I call it? Faculty, right? So the name comes after the structure, and I put a semicolon after it, because it is a type def, right? You're defining a type, just like an enumerated type. Now, unlike an enumerated type, where you provide a list inside the curly brackets, here it's not really a list. It's a bunch of variables, right? And the order generally does not matter, but you do want to, for organization purposes, you want to impose your own ordering. And since it's not a list, we do not list these things using commas. Instead, we use semicolons. Right? So the first one that I'm going to put in is my name, the first name. I want to model this data over here. First name, last name, NUID, city, state, and office. Okay? So let's go ahead and do that. What is a first name? It's a string, right? So char star, first name. Right? Note here I'm following a lower camel casing convention, just like I've been doing on all of my variables so far. Right? Char star, last name. I could have gone with the first and last, but first what? Last what? Right? So I'm going to be more descriptive here. And again, notice what I'm doing here. Semicolons at the end of each of these. Okay? If you wanted to go last name, then first name, that's up to you. But again, it's not a list, so there's no ordering to these things. Now, under the hood, the order does matter, but that's really only if you're going to have static strings, and in which case you need to put them at the end or whatever. Don't worry about that, though. We're not going to do static strings. Okay? What else is in there? My NUID. So what type is an NUID? Integer. Okay. Now, you do have to be careful, though, because some NUIDs do begin with a 0, right? So maybe you have an argument for designing this so that the NUIDs are strings instead. Because when you go to print it out, of course, you'll want those leading zeros. How many people's NUIDs start with a 0? One, at least 10% of you, so I'd say at least 2 or 3 people in here. Right? How many people have an NUID that starts with 2 zeros? All right. Yeah, that's a 1 in 100 chance. Right? They are randomly assigned. Okay. City, state, office. Right? Those all sound like strings. City, char, state, char, office. And just for variety here, let's go ahead and add in some sort of a double, right? To show you that you can also use doubles inside of this thing. what would it be? Usually I go with students, and so I do a GPA. But what?
Height.
Height? Okay. Height, how? Centimeters, inches, feet? Feet, inches?
Miles.
Meters? Let's go height in millimeters.
Miles.
Meters. Let's just go meters. We do want to make sure that we're using scientific units all the time. Right? Never ever write a program that doesn't use, not in the military, or what? All right, so I'll put all those things. But you know what? I also want my, say, date of birth. Date of birth. What is a date of birth here? An array of what, though? Integers? So you want to split it up into how many numbers? 3. So date of birth, say, month. Date of birth, year, and day. All right. All those would be integers, integers, integers. Okay. Is that the only way that you can, that you have to model time? Yeah, how have we used time before? So there is a built-in type called date_t. Don't use it. It's not interoperable. It's kind of hacky, whatever. But let's think about other ways that may have used time. Right now, what is the Unix time? Yeah, there's the current time right there. It's one number. That's the number of milliseconds since January 1st, 1970, right? And that's called the Unix epoch, right? So you can go ahead and convert whatever time you want to just one single number. Now, what about going back in time? Negative values. What happens when we reach the limit of this number? Oops. Yeah, another oops, right? It's the 2032 problem.
Oh, that's soon.
Yep, it is very soon. How to 2030 isn't it? Yeah, 2038. Sorry. All right, you got 6 more years now. All right. There we go. The 2038 problem. What the problem is that when you hit, if you're using a 32-bit signed integer for Unix time, that's when you reach the limit for the number of milliseconds since 1970. At which point it'll become 1901 again, or something like that, right? Nobody learned their lesson with Y2K. Don't worry, I don't think that there are any 32-bit Unix systems out there. You're talking about old garbage. Although I take that back. There was an article today about the IRS still using 60-year-old mainframe software and hardware to do tax returns. Most of the nuclear systems are also still on really ancient hardware, which is probably a good thing because then it can't really be hacked. Right? Question over there?
I was going to say that our systems either in the process of or already have switched over using long 64-bit data types.
Yeah, most of them are going to be. Yeah, and that means that let's see, Wolfram Alpha. If you use a 64-bit integer to denote the number of milliseconds since 1970, then you only have until milliseconds to, let's go years, right? You only have about a couple billion years. Millisecond, come on, yes, that's what I want. So convert it. Incompatible units, okay. How is it? All right, whatever. I bet Google can do it. Milliseconds to years conversion tool.
So
yeah, go ahead.
that's 64-bit time?
Yeah, that's 64-bit. Y minus 1 because you start at 0. Y only 63 because you need a sign bit, right? So there's the number of milliseconds. Milliseconds to years. Can you do it now? There we go. So you've got 292 million years to go before you reach that problem. Right.
That's nice.
That's nice, yes. Right. So that's one other way of representing time. Here's another way of representing time. As a string. In fact, that's an ISO, not that, but ISO 8601 format. Right?
So in C, is there like a system time thing?
Yeah, date_t.
Like to get the
Yeah, it's I forget what it is, but yeah, you can get the current time. In fact, I think it's just time, and it might actually require you to give it a. Yeah, you can do that. That's how we seed the random number generators in some sample code that we've given you before, right? Here's the ISO standard. Right, come on. Oh, all right. I want the Wikipedia version. I don't want the. There we go. It's just so that you can see what it looks like. It's a string, no spaces, and it is lexicographically orderable because there are leading zeros. Because the year is well formatted, always to have 4 years, 4 numbers, 2 numbers, 2 numbers, and separated by time, and then it's a Greenwich mean offset. So it's a universal way of representing time that is also lexicographically orderable. If I've got 2 of these strings, all I have to do is do a string comparison, and if it's in the future, or if this time is in the future relative to this time, then the strings are also orderable, right? So very, very clever way of representing time that is also orderable if you treat it as a string. Right? So seeing those 3, which one do we want to do?
Probably the string one.
Okay, I would do the string one as well, right? But for variety, let's go ahead and go with the first answer here, where we keep track of those 3 numbers. Right? But you know what? 3 numbers? 1, 2, 3. Multiple pieces of data that represent one logical thing, a time. What should we do with that thing? Encapsulate it, right? And create a structure, right? A type def struct, right? And we'll call it a date, right? Because that's what it is. Now, date of birth is way too specific, so I'll just go ahead and go with month, day, and year. Right? Because this could be something other than a birth date. It could be a higher date, right? It could be whatever. In fact, that's what I'll do. Instead of a birth date, I don't want to tell you my birth date, right? I'll go ahead and go with a higher date. Right, there we go. Right? I don't want to tell you how old I am. I'm only 29. All right, is that going to work? Let's find out. Demo.c. Uh-oh. Unknown type date. Why is it unknown? Because it's below. In C, you have to declare variables before you can use them. Likewise, if you're going to use a structure and then use it, you have to declare it beforehand. Right? We use it down here, and so therefore it needs to be declared up here. Order matters.
Can you do
There we go.
prototypes in terms of structures?
No, prototypes are only for functions.
I mean, can you do something similar?
Not really. You usually will eventually put this into a header file and include that, but that's a few steps ahead here. Right?
That still needs to be in order, right?
Um,
In the header file?
yeah, it still needs to be in order in the header file. Yep. You can do extern or static declarations, but that's beyond this class, right? Okay. All right, great. So we've got one structure here that represents a date with 3 numbers, and another structure here that takes a bunch of pointers to arrays of characters, a double, but then also refers to another structure. In other words, this faculty structure is composed of other structures. That's called composition. When you've got one object, one thing that is composed of other things, composition, right? Okay, that's good enough for now. So let's go ahead and observe what we just did, okay? In fact, I'll go ahead and make sure that you have this in your notes. Let me go ahead and cut and paste this. And put it in the notes here. There we go. So let's make some observations about what we did. A structure is composed of multiple pieces of data, or even other structures. This is called composition. Right? And it's also used in object-oriented programming languages. The order of declaration matters. Right? If you use a structure in another structure, it must be declared above. Right? Each variable inside a structure is called a member variable. Or sometimes people call them components, because eventually we're going to talk about new syntax here, the component selection operator. But we'll just call them member variables. Right? You may want to designate some unique identifier for each possible instance of a structure. Now, what do I mean by an instance of a structure? What I designed here was just the declaration of what a structure is. Have I actually created any faculty in my main program here? No. So let's do that. Faculty, me, right? Chris. I'll just go Chris. There we go. And I'll leave it like this. Okay. Now that creates an instance. That instance has values for all of these variables. If I were to print out my first name right now, Chris, printf, hello, %s for the string, Chris, how do I get to my first name? You use a dot operator, Chris dot first name. In fact, I'm not even going to call it Chris anymore. I'm going to call it me because I don't want to confuse Chris, the variable name, and Chris, the string value here. Okay. So is this going to work? Let's find out. What's it going to print, do you think? Segmentation fault. Why? Did I set my first name to CHRIS? No. In fact, what is it? It's a pointer. What pointer value does it have right now? Who knows? Dead beef, right? It could be anything. In this case, it's going to end up being a segmentation fault because it was an uninitialized pointer. Okay, fine. Let's go ahead and set my first name. How do I go about doing that? Well, if I'm going to dynamically allocate it, what do I need to do? Me.firstname is equal to a call to malloc. Right? Char star malloc. Right? How do I create a new string variable? Size of char. And how big do I want it to be if it's going to be CHRIS? Y6, the null terminating character. All right? So I'll go ahead and go with 6 here. Now, does that put Chris into my first name? Me.firstname. First name. I can go ahead and set it equal to Chris, right? Is that the way that we assign strings? Nope. How do we assign strings? strcpy into my first name, the value CHRS. And now this should work. There we go. Hello, Chris. Right. I've got a lot more work to do here. Last name, NUID, city, state, office, etc., etc., etc. Right? So let's go ahead and start the copy pasta. Copy pasta. Last name and BOURKE. So 6. Just do 20. Okay, fine. My last name is. Why did I do 7? Null terminating character. So there's my first name. There's my last name. Now what about my NUID? Me.NUID is equal to. Oh, I got myself into a problem already. This is why we don't copy pasta, right? I created enough space for my last name, but where did I copy my last name? Into my first name, right? Don't copy pasta. 1, 2, 3, 4, 5, 6, 7, 8. I don't think that there's a security issue with telling you my real NUID, but whatever. Right? There we go. Did I have to do a string copy there? No, because it's an integer. I won't worry about city, state, zip. In fact, I can go ahead and comment those out for now. And how many meters is 5.9? 5.92 meters. 1.7526. The 2.6 is important there. Me dot height is equal to, there we go. Always around, I'm 2 meters, okay? Geez, what would 2 meters be? 2 feet?
It's taller than 6'2".
Oh, wow. 6'7"? All right. Join the basketball team. All right, there we go. What about my hire date? I've been like here for 11 years, so let's just say that it was like July 1st, 2010 or something like that. So July 1st, 2010, or yeah, 2010. Me dot. Right. The dot operator is the component selection operator, but we just call it the dot operator. Why? It's a dot. Right?
Component selection operator.
Yeah, component selection operator is way too many words, right? My hire date. So hire date. Hire date is equal to, right? Yeah, I have to add another dot. Why? Hire date is another structure. So my day that I was hired was, say, the 1st of July. Me dot hire day, date dot month was the 7th of July, the 7th month, July, and me dot hire date dot year was 2010. There we go. Wonderful. Well, one faculty member does not a department make, so let's go ahead and make another faculty member instead of me.
Not me?
Not me. Give me another professor. Let's just go with a real person, real historic person, Grace Hopper. So Grace, right? Now that's 1, 2, 3, 4, 5. Oh, we have the same number of letters, so that's good. 6. Hopper, Hopper. That's one. Oh, wow, we have the exact same number of letters in both of our names. Wonderful. She has an NUID of 1112222. Okay. I have no idea what her height was. We'll just say that she's a little bit shorter than I am, right? Right. And what it was Grace Hopper's birth date. Right. She worked on one of the first programmable computers. What was it called? The Harvard Mark I, used in World War II as part of what was the Manhattan Project. Doing calculations to ensure that the implosion device would actually work. But they were never actually told what they were computing. They were just told, compute these calculations, and we're not going to tell you what they're about. Right? So December 9th, 1906. Right? She's long past, but December 9th, what did I say, 9th? Sorry, 9th. So 12/9/1906. There we go. Make another. Should I copy paste? Should I copy paste? Probably not. Right? Let's rethink this. Before we do, let's come back over here and add to our observations. Right? To get a single component, that is variable, in a structure, you use and we called it the component selection operator, or the dot operator. Okay. What about their styling so far? Styling. The names of, say, structures should use an upper camel casing convention. Built-in structures in C, note, this is not something you should do yourself, it's just something you should know about. Internal structures in C use a foo_t naming convention. The _t there is type, right? So for example, date _t, right? Time _t, right? And a couple of others. Those are built into the standard library, and that is its naming convention. If you use that naming convention, people will think that that's a built-in type that's part of the C standard or part of the C standard library. Don't do that. right? You're not writing for the C standard library. You're writing your own structures. So my suggestion is to use upper camel casing. If you want to, you can use lower camel casing, lower underscore casing if you want to. A lot of people do, but I would just recommend upper camel casing because it's a modern convention. Okay. Member variables use a lower camel casing convention. Right. You use type def struct with the name at the end, followed by, or terminated by, I should say, terminated by a semicolon. Right. Typically, usually, structures are declared in a header file, right? With an appropriate name. Appropriate name. Okay. So that's what I'm going to do now before we move on to improve the code that we already have here. What I'm going to do is I'm going to create a brand new file. I'll call it faculty.h, right? The header file. And reload this. There it is, faculty.h. And I'm going to go ahead and get rid of all this data files now. And I'm going to move those declarations over into faculty.h to document these two things, right? So what is this? Well, it kind of tells you what it is. Models a date according to the what's the calendar that we're on? The Gregorian calendar, or Gregorian is it? Gregorian, yeah. Models a date in the Gregorian calendar, right? It's not a date in the Chinese calendar. It's not a date in the Julian calendar, et cetera, et cetera. Right? Julian would be with only 10 months, right?
I think that was the one before Gregorian.
Oh, well, yeah. The one, was it Julian then?
I thought Gregorian only fixed leap
Was
years.
the one created by like Caesar and Augustus, and like the Gregorian calendar was like modified by like the church.
Oh, okay, in the Middle Ages probably sometime. Okay, all right, sure. History, wonderful, right? Anyway, models a faculty member at PKI or something like that. I don't know. Right. Go ahead and add your own documentation in there. Okay. And I just got rid of these because I just want to keep it simple. Okay. Now over here in demo, I don't redeclare those. Instead, I just include my own file, faculty.h, just like you've been including header files with all your prototypes. Okay. Now again, my observation here is, you know what, I'm going to be able to create a lot of faculty members, and do I want to be cut and pasting like a dozen lines of code here over and over and over again? Probably not. So let's come over here to faculty and think about what kind of a function we could write that would manufacture new instances of faculty. Me, Grace Hopper, Herbert, Lim, and now I'm out of names that I know here, right? In an object-oriented programming language, they call it a constructor because it constructs things. Here, I'm going to call it a factory function because it manufactures things, right? Different term, just to draw your attention to the fact that this is not an object-oriented programming language, okay? So I'm going to go ahead and call it create faculty, right? Yeah, I spelled it right. Okay, there we go. What should it take as its input? All that stuff, good, right? In fact, I'm going to make them const char star first name, const char star last name. Right? Why am I doing const here? I'm going to give you the first name, and I'm going to expect you to do a deep copy of that first name, because I don't want you once it's created. I've got chris over here. I don't want you mucking with my data over here. I want you to go ahead and create a brand new independent instance of that faculty member. Right? First name, last name, int, NUID, height meters. I'm kind of regretting doing that now. Double height meters. Right? What about the date? One way that we could go is, in fact, you can break this up. In fact, this is usual. to break up long lines, you just go ahead and align all of those parameter variables. So one way we could do this is a date of hire. Right? I'm just drawing your attention to the fact that the hire date and the date of hire, they're different variable names. Right? Or we could do, say, date or day of hire, month of hire, and year of hire. Right? Now, neither one of these is wrong, neither one of these is right. It is a design decision that you now have to weigh the consequences of. What about the first one here? The consequences of that is you have to create a date before and then give it off to this other function, which means that maybe you also want a create date function. Right? The consequences of this is that, well, now you're requiring the person that is creating a faculty member to break up their date, right, into 3 components. And also they have to remember the order: day, month, year. In fact, is that the right order? That's the American order, which is not right. Is that the right order? That's the European order. That is not the right order. That is the right order. Why? Because it's lexicographic, right? All self-respecting computer scientists who have ever had to deal with strings and ISO 8601 format will agree, right? And you can always tell a computer scientist by the way that they write their dates. Right? So it's a shibboleth. Have you ever heard that term before? A shibboleth? Shibboleth. Well, the way that you pronounce it, I think it's a Hebrew term. The way that you pronounce is any custom or tradition, usually a choice of phrasing or even a single word, that distinguishes one group of people from another. I don't have a drink with me, but usually I have, a Diet Coke. Oh, there we go. Well, no, that's tea. I don't see anybody having would you call it pop or soda? There, what is that thing over there? Yeah, okay, generally? Soda, okay. Does anybody say pop? All right, vast majority probably in the Midwest would say pop, right? I think it's a Southern and East Coast thing to say soda, right? Something like that. That's a shibboleth, right? If you ask somebody what is this thing and they have a particular word for it that is from a particular region, that's a shibboleth, right? What about, let's see, does anybody have any database experience? All right. So another shibboleth that I've found in computer science is Microsoft SQL Server. Right? Pronounce that right there.
MSSQL.
Oh, okay. You went completely 2 different other directions. So if you're coming from a Microsoft background, here, let's just shorten it to SQL. Right? If you say SQL, I know that you're not from a Microsoft background. Right? If you pronounce it SQL, I know that you're from a Microsoft background, right? Because that's how they all say it, SQL Server, right? SQL, no, right? That's another shibboleth, right? So, wow, getting really off topic here. But anyway, back to the design decision here at hand. Which one do you want to do? Second one? Okay. Again, it's not right, it's not wrong, it's just that you're going to have to deal with it differently. And in an object-oriented programming language, you can define multiple constructors so that you can give them both options and be more flexible. Okay, that's good enough. What is my return type here? Am I returning an integer?
You should return a faculty, right?
Okay.
Can you return a faculty?
I've defined it, so why not?
I suppose.
You could do that. Should you do that? So let's come up here and look at faculty.
Oh, you need a...
Char star is a pointer. That's 8 bytes. Another pointer is another 8 bytes. I'm up to 16 already. Integer is 4 bytes. That's 20 bytes. Double is another 8 bytes. That's 28 bytes. Date is 3 integers, which is 12 bytes. And I've already lost count here. Right? I'm returning something like 40 bytes instead of a standard, 4 bytes or 8 bytes or something like that. right? That's not that big of a deal with this kind of structure. But what if you've got a structure with, say, 20, 30, 40, 50 different fields? Right? First of all, rethink what you're doing. But second, it gets kind of unwieldy, right? And that's a lot more memory, okay? When you are returning this, you are basically returning it by value. You are copying that entire structure onto the stack and returning a pointer to that stack memory. We like to stay away from the stack. So instead of a faculty member, I'm going to return a pointer to a faculty member, okay? That means that I'm going to have to dynamically create a faculty member, an instance of a faculty, populate all of its fields, and then return a pointer back to it. Let's do it. Touch faculty.c. Don't touch the faculty. All right, so let's copy this over. Do I have to copy my definitions for the structures that I just made? Nope. What do I do instead? I include faculty.h. And now it knows what you're talking about. It knows about faculty, it knows about dates, etc. Okay? All right. I want to create a brand new faculty member. If I do it like this, faculty F, and then I return F, is that going to work? Yeah, okay. Let's go with, it's not going to work. Why? Because, well, I need a semicolon. But this is a regular old faculty. What's the return type here? A faculty pointer. So your first solution might be to say, well, let's go ahead and turn that regular old variable into a pointer with an ampersand. Is that going to work? Remember, where is this being allocated? On the stack. Inside your stack frame for this function call, right? Remember how it works. Function calls function calls function. When that function returns, what happens to that function's stack frame? Popped off and it dies. So this faculty here is no longer in scope. Right? So what do we need? A dynamically allocated faculty with malloc. Right? So malloc. Right? What is my cast going to look like here? Faculty star. Right? Why? Because that's what we're doing over here. Right? Just yeah. Sorry. What? Yep. It'll still be removed. It still exists in the stack frame, and the stack frame is now gone once you return. Right? You have to do it on the heap, somewhere on the heap. So just think about all that you've done so far with dynamically allocated arrays. Int star, double star, char star, right? You've defined your own user-defined type here, faculty. So everything that you've been doing up to this point with the regular primitive types that are built into the language, you can now do with your user-defined type here, this structure. Right? So faculty star, malloc, how many bytes do you want? Size of faculty. Right? Exactly like you would with an integer, exactly like you would with a double. And how many of them do you want? Just one of them. It's not an array. I just want one. You don't have to do that, of course, but I'm doing that to emphasize the fact that there is only one being allocated here. Okay? All right, so let's come back to our demo here and cut and paste all of this stuff. Let's see over here. There we go. So we no longer have me. We have f.firstname is equal to, and it's not necessarily 6. What is it? It's how big is first name? strlen of first name. My first name was chris, but did we allocate only 5? Nope. What do we need? +1. Man, I really wish I had kept that deep copy string function that I wrote a while ago, right? Reuse the functions you've been writing in class, in your labs, and in your hacks, right? And then copying over into f.firstname, By the way, this is wrong, but we'll find out why it's wrong here in a moment. First name, there we go. F dot last name, and it's not 7, it's strlen of last name plus 1, there we go. And it's not necessarily Hopper, it is last name, F dot last name. Now, do I need to do any dynamic memory allocation for an NUID? Nope, just do that NUID. No dynamic memory allocation for the height, although I don't think height meters, there it is. Was it originally height meters? Yes, it was. Okay, so I need to make sure that that's correct. There we go. And it's not always going to be July 1st, 1906 or whatever. All right, her birth date was her hire date. All right, it'll be day, right? Or year of hire, month of hire, and day of hire. There we go. And then I return F at the end, making sure to F instead of me. There we go. Okay. Let's try to compile this now, right, with the wall flag. And I'll just try to compile it because I'm only trying to compile this faculty.c file here right now. Faculty.c. It's going to fail. Let's go all the way up here and find out why. In fact, I'm going to go ahead and clear this out so that we don't have old messages here. There we go. All right. Implicit declaration of malloc. So what's my first problem? Include the standard library. I'm also doing string stuff down below. So what else should I include? Include the string library. All right, there we go. Otherwise, those were just warnings, right? And I would get away with it. There's my first actual error. F is a pointer. Did you mean to use, and ignore that for a second, okay? F is a pointer. I cannot use the direct component selection operator, right? What do I need to do to access the first name of this faculty member? Dereference it. And how do I do that? Star F. And then I can go ahead and go dot. But if you look at your table of order of precedence operators that you can find on order of precedence operators, C, right? You will find that the dot operator has the structure and it has a higher order of precedence than the dereference operator. So let's read this as it would be evaluated. First of all, it's going to evaluate that dot before it evaluates that dereferencing. That's a problem that is easily fixed by putting in parentheses here. That's sloppy. And they realized it was sloppy. So they introduced more syntax. F, arrow. Right? That's the indirect component selection operator. Right? But we call it the arrow operator. Why? Looks like an arrow. Right? Anywhere you're using a dot, now because you've got a pointer to a structure, you now use the arrow operator. Right? Arrow operator, arrow, arrow, arrow. Oh, what was that? What was that trick to do block selection?
Option, shift, click, and drag.
Option, shift, click, and drag. Nope. Option, shift, click, and drag. Hey, there we go. I like that. Option, shift, click, and drag. You put that on a Post-it note and you stick it up until you burn it into your brain, and then you can take down the Post-it note. All right? Excellent. Now let's see if that compiles. Yep. Everything's fixed. Okay.
Will it throw warnings if you do the pointer, the asterisk?
What do you mean?
Like if you try to go star F dot whatever, will that throw?
It will. Oh, like if you do it wrong, like star F dot first name. Let's do NUID because I don't want another pointer. NUID is equal to 1, 2, 3. Let's find out. Yes, there is. F is a pointer. Did you mean to use the arrow operator? Nice. Very nice. Now, of course, if you surround it with this, then you probably won't get that warning. In fact, it's an error. Weird, right? You won't get this because that's correct.
That's nice.
Yep. Nice. I'm actually really impressed. Good job, GCC. That is an error. Right? Okay. Let's go ahead and go back to our demo, and now we can use that factory function to get instances of me and Grace. Right? Create faculty, right? Chris, last name Burke. What else do we want? NUID, height. So there's my NUID. There's my height. There's my, what order was it? Unfortunately, that's a consequence of our decision here. What was the order again? Well, again, if you're a self-respecting computer scientist, you're always going to go year, date, month, or year, month, day, right? So, 2010, 7 and 1. There we go. Okay. And then I can have a print out my information or something. Let's go ahead and grab Grace here. Right. Create faculty, Grace, comma, Hopper. And I'll just make up a different one, 1, 2, 3, 3, 2, 1, 1, 2. She was what, 1.5 meters, we said, 1906, and 9 and 12. Or I guess it was December 9th. Doesn't matter. So I'll just fake data. There. Now what we had before was two big giant chunks that we repeated. This is much better. Why? It's reusable, right? It's testable because we have it in one logical unit. And it saves us on a whole bunch of code, right? We've encapsulated the code inside of a function. Okay? Now, is this going to work right here? Me dot first name. Me, is that a regular old structure? Nope. So I need an arrow operator here. Now we can go ahead and combine all of these things in, and let's print out Grace's first name too. Hello, Chris, and Grace. Grace, first name. There we go. Oops. Whoa, I don't know what happened there. GCC faculty.o. Remember, because we already compiled that into an object file, and demo.c. Let's make sure that there are no warnings here. There are none. Right? And run it, and we see hello, Chris and Grace. Okay. So I've got the start of a good design for a structure to represent faculty. I've got this nice creational function. This is a factory function, right? Let's go ahead and again note what we've looked at so far, right? Using structures. Right? Once defined, a structure can be declared like any other variable. Right? Say, for example, faculty F, right? Or a pointer to a structure, faculty star F. Right? You can and should design and implement a factory function to make creating instances of a structure easy, right? When you have when you have a regular old structure, you use the dot operator. When you have a pointer to a structure, right, you use the arrow operator. Right? And again, you can use the dereference inside parentheses and the dot operator if you want to. That's a mess. Just use the arrow operator. Okay. Let's see. You can dynamically allocate a new structure using malloc and size of, right, with your structure. Another, again, the example would be size of faculty. Right, there we go. Why didn't I have to do that with the date? Let me draw your attention to what we were doing. I had to use an arrow operator here with F, right? Why is that? Because it's a structure pointer. Did I have to use the arrow operator here for the day, the month, and the year? No. Why? It's not that. It's not a pointer, right? It's just a regular old structure. If it were a pointer, it would look something like this: date star, and then I would need to use the arrow operator. But it's just a regular old structure here. Okay. Let me show you some alternative syntax while we're at it. And for that, I'm going to go ahead and bring up pythontutor.com. Right? And there's my structure definitions. I'm going to go ahead and create a faculty without using that factory function here. And let's go ahead and visualize what that looks like. Right? Come on. Any questions while we're waiting? No? All right. So there's a good visual representation of this thing. It is a box that holds stuff. It holds multiple pieces of data. It holds a first name, which is a pointer, a last name, which is a pointer, et cetera, et cetera, et cetera. It holds a higher date here, which is another box. So we've got a box within a box. That box contains three things: a month, a day, and a year, which are all integers. Right? So think of composition as a box within a box within a box, right? It's a way of organizing things. Let me edit this code further and show you, if you need a quick and dirty way of initializing a structure, you can use the same syntax that you would use when you're initializing an array with values. For example, when we did the primes array, right? Primes, square brackets is equal to, and then curly brackets, and then a list of the values that you want to put in that array. You can do a similar thing with structures. If you just want, say, Joe Smith, and then what's the rest of it? 1, 2, 3, 4, and the height 1.25 meters, and the higher date of, how do I do a higher date? If it's a box within a box. More curly brackets, another box. And that's going to be there. Now here, order does matter. So if it's month, day, year, then you need to do, say, what is today? The 4, 6, and then 2022. Right, there we go. Let's visualize that execution. Hopefully it works. I'm pretty sure it should work. There we go. All right, and let's go to the next. And you see it's all been initialized in one line. Okay? That's only if you need a quick and dirty example, right? For testing purposes or something like that, right? If you are actually going to use this in practice, then you still want to have some sort of a factory function to manufacture these things, okay? But there's Joe Smith, and then all of these boxes are now filled with those values that I gave it, okay? And again, it's the visualization that you should have is a box, and then it's composed of other boxes and stuff like that, okay? I'll edit this code and make sure that you have it. You can use the curly brackets to initialize a quick and dirty structure for testing, right? And there you go. Right? We say it's dirty because you don't want to do it, all the time. Well, sometimes people refer to those as constructors, like you did, but that's usually for an object-oriented programming language. What's the opposite of construction? Destruction. Often, you can write and implement other helper functions. other convenience functions. For example, a destructor, right? A way to clean up, in other words, free a structure. Right? Destructor, it auto-corrected here. Destructor. You. I don't even know if that's a real word or not. Yeah, it is, a destructor, right? A way to clean up or free a structure. A function to print a structure in a human readable format, right? What other functions would you like? What other functions would be, you know, useful when creating structures or using structures or something like that? Any? Well, I said print a structure in a human readable format. Where else would you want to print something? Maybe to a file, right? Maybe you want to serialize your structure to a JSON format. Maybe you want to serialize your function to an XML format. Maybe you want to do a whole bunch of other things with your structure. Right? We will do as many of these as you want, right? So serialize to a JSON format, or more generally, a toString style function. That here's your structure, go ahead and format it as a string, and then I get to decide what I want to do with that string. I could dump it to the standard output, I could dump it to a file, I could dump it to a serializer, I could do whatever I want with it. Right? So as our last thing today, let's go ahead and write this destructor. Right? Let's go ahead and get rid of this. Right? What do we call our destruction in C? How do I destruct or destroy an array?
Free.
Free. So let's go ahead and free faculty. I don't know, fire faculty? Free faculty. Right, there we go. So am I going to be returning anything?
Nope.
Nope. What am I going to be taking? A faculty F. Statically allocated faculty. There's no reason to free that up because it's on the stack. Right? The stack will free that up when it gets popped off. So really you're only destructing or freeing faculty when you've got a dynamically allocated one and you've got a pointer to it. Okay? By the way, you can make them const, but should you in this case?
No.
Because you are going to be making changes to it. You're firing them. There we go. What else should I put in here to do? It's a header file, so what do all prototypes need? Documentation. There we go. Okay. So as our last thing today, help me write this function. Free this faculty member up. Right? Well, I could free F. Let's see if that works. All right, it's over here. It's already included. I'm just printing you guys out, me and Grace, and then let's fire ourselves. Free faculty, me, and free faculty, Grace. There we go. GCC. I'm going to do it all in one shot. Generally, you shouldn't do this, but we're short on time. So demo.c. There we go. Were there any problems? Nope. Run it. Looks like it works to me. Right? Except then when I put it on the grader and it fails, because I didn't do enough rigorous testing, what's my next tool that I need to bring to bear? Valgrind. A.out will tell me that there are errors that they're not manifesting. And in this case, what are the errors? Definitely lost, record 404. Definitely lost, definitely lost, definitely lost. What do I have here? A memory leak. Right? All the way at the top here. 4 blocks. And of course, it's not going to tell me the line number. It's just going to tell me this memory address. What should I have done to make sure that I've got those line numbers?
Compile it with G.
G. Then rerun valgrind, and now it will give you the line numbers that it's happening on, right? You created these things using malloc. Come on, right? Yeah, what did I not clean up? The internal char stars. Remember, We called malloc here, here, and here. 3 calls to malloc means 3 calls to free. Right? So if you're going to free up the faculty, you need to free the faculty's first name. F.firstname? Is that right? Do I have a regular old structure here? Or do I have a structure pointer? So I need an arrow. And if I created a first name, certainly I created a last name. And I need to clean up that next. Recompile with the G flag. Again, run it to make sure that you didn't break anything. Still runs fine. Now run it through valgrind and it'll tell you 0 errors, 0 context. Now it's lovely. Right? Okay. Remember, run valgrind. Right? If you ever get invalid free or double free or invalid pointer or some other error like that, in your own tester, you need to be running valgrind and it'll tell you exactly what's going on. Right? Not exactly what's going on, but it'll give you some hints that you have an invalid read or an invalid write or something like that. Okay? All right, any questions? Yeah, go ahead.
I have it's not about structures, but it's just like in general about
Okay.
So like, if I'm like writing a program and it's like I'm like messing around with like bits and stuff at a bit level, is there any way to like see that in this compiler, or like what's the best way to like see?
GDB, probably. So give me an example of what you're doing.
Well, like I think the one program was like that I had to write was write a program that toggles the bits of whatever. So like.
Let's go with 7. All right.
Mm-hmm.
7 and then 5. Right. And then int z is equal to x and 7. What value is that going to be?
Whatever 5 and 7.
Some whiteboard stuff.
Whiteboard.
7, 5 is going to be what? So, and those together, these are all zeros. So this is going to be 1, 0, 1, which is 5. That's not what I wanted. So let's go ahead and go with or. What's that going to be? 1, or sorry, no, or. Now that's not what I wanted either. Yeah. What is it? Caret. Good. This is exclusive OR, so this will be
0.
0,
1.
1, 0, but these are all zeros. So it's going to be all that. Right. So what do you want to do?
Caret.
Okay. And we'll print Z, print F. We'll print it as a variable here, Z, G, run it. There we go. Oh, it is 2.
Oh, next one, if they're both zeros, it's still 0.
You're right. Duh. Okay. Yes. Thank you. So 2. Now you might ask, well, I want to see the hexadecimal or the binary or.
Yeah, I want to see like just what happens, like if it, like how it changes to make sure it's.
No, it's X.
Can you print binary GDB?
Nope. Well, 2 is going to be 2 in hex. Give me something.
37.
I don't know if this is correct or not. There we go. There's the hex. Can you print in binary? No.
Well, you can make a function.
You can make a function to do it and convert each one of those hex codes to a binary string if you want to. No, maybe GDB does. Let's go ahead and do it. GDB a.out. Layout source. Break. I don't break at main. Run. Next. Print X. Print Y. Print F. %H or X. Nope. Okay. Printf style in GDB. Part 1, part 2, multiple parts. All right, at this point, you can Google as best as I can, right? Print f percent x. No, that's not gonna work. P space P space backslash T.
Yeah, the variable name.
/T.
I think P is the variable name.
Forward slash
Short for
T
yeah, but
Yeah.
then space, and then your variable.
X. Oh, there you go.
There you go.
So you Googled it and you got it. Do the same thing for P /T Y. There you go. Now, careful because they're not aligned. So you might want to look up like some modifiers there to get leading zeros because there are no leading zeros here and it won't align up. And then if I go next, now Z has been set, so I can do the same thing, P /T Z, and see that it looks like that.
I mean, you can write the whole print if you want, but
Yeah. That's all P is doing, print. All right. /T is binary. All right. /H would be hex. Nope. Size letters are meaningless in print. But all right, I don't know.
Meaningless.
But there you go.
If I start like messing around with like the ports on like a microcontroller or whatever, there's no way to see that on this. Like I'm just no.
What do you mean? I mean, you could,
It's like I program microcontroller in C,
right?
and I like upload it to this, and I like want to see like if I start like messing around with like different ports and stuff on the microcontroller inputs and outputs like in C, would there be any way to see that on here or not?
On like the Visual Studio Code,
Yeah.
the microcontroller is not going to be there, so there's no it would fail to connect to your microcontroller immediately, right?
Okay.
If you had a microcontroller simulator or something like that
Alright.
on there, then yeah,
Okay.
you might run your own simulator. I don't know.
which development thing did you say to use?
He has this use DVR Studio.
That one's way better.
Okay.
I don't like DVR